As you probably have heard, this is the first time we've actually done a two-day conference. And so it's, 2 days is more than 1 day plus 1 day when it comes to all of our schedules. So I'm very pleased that people are here. I do want to give a plug for Ron and the forestry panel that's happening at the end, and for all. So they will greatly appreciate your attention through to the end. I would also like to take the opportunity. I woke up this morning and realized happy summer solstice, happy National Indigenous Peoples Day, which falls on the summer solstice, and happy to celebrate that on the land of the Leguangan peoples. So, I was wondering when evening was going to come last night. It just stayed light, and I said, "Oh yeah, of course, it's the summer solstice." So, we'll get straight into. Oh, one other thing I was asked. I think there are 10 new fellows who received certificates but didn't sign the book. Or if you are an existing fellow and just didn't happen to have got around to signing the book, please, at the reception area there, it's nice. It's sort of like the ledger of fellows of the Academy. So that'd be great. As they say, with no further ado, I'd like to jump into the first panel, and if I can ask my co-panelists to come up to the stage. You're going to see a bit of me up here today. So one of the things we talked about was these programs that the Academy has set up, and this is the one on future networks. Now, Dr. Lin Kai and Dr. Song Guo, Lin just joined the Academy, and Song is, we've got a group that's been working on this, and then they have not been involved directly. Leon-Garcia, who many of you know from University of Toronto, is actually what I would call the research lead, the PI on this program for the Academy. And he is in, I don't know if he's in Barcelona or Madrid, but he's somewhere in Spain. So, and he sends his apologies. His paper was accepted and he had to go. But he will be coming in via Zoom to talk. So I'll be asking him to talk first to sort of set up what the Academy's been working on. So I'm going to say a few words, have Al say his thing, and then we're going to hear from Lin and Song on their work, which, interestingly, was very well aligned with the directions that we're going in. So, if we can go to the next slide. Yep, next one. Okay, can you make it bigger? Yeah, when I say make it bigger, because like on the screen here, there's a bunch of space for text that I don't have, and therefore I have to sort of, and it's the wrong distance for these glasses. Okay, so one of the things I just wanted to say in starting off, it's another weird birthday this month. The internet is 40 years old, and that's marked by the date that ARPANET moved over to a TCP/IP protocol, if you're a telecoms person. And the funny thing about 40 years, I've actually been a professional engineer now for 42. So it's kind of the length of what I regard as the length of an engineering career. And it makes you think a bit about the things we've been talking about yesterday and we'll be talking about today, of what the next 40-year pitch is, what is going to be, you know, it doesn't matter if you are a telecoms person or a hydrogen power person or something. The internet has defined your space for the last 40 years. I think some of the topics we're talking about are going to be as ubiquitous for the next 40. One of the things that is very different, and many people don't understand, and unfortunately even some of our regulators don't appear to understand, is the internet today is extremely different than it was 5 years ago. Okay, so you get a bunch of different numbers on it, but you know, you've probably heard of some of these small companies like Amazon and Google and Microsoft and IBM, which are referred to as hyperscalers. And what's going on behind is there used to be these little islands of data centers connected by the telecoms networks, and they got bigger and bigger and bigger. And so now, you know, Google has maybe the biggest fiber optic network spanning the world and its various centers. So 3/4 of, say 2/3, 3/4, pick your number, of what I would call traffic miles is actually not on the public telecom networks at all. It's flowing around within the hyperscaler networks, which are not configured the same way as each other. They use some telecom equipment and they use some other stuff, but it's just in terms of managed traffic, it's become a very heterogeneous network, and that brings about risks and opportunities. But one of the risks globally is that the network starts to break up and become a series of islands. And so one of the big discussions at the moment, you know, it's not obvious that we have almost ubiquitous access to the internet. And so one of the big questions that's going to happen going forward is, does the network break into a bunch of what I call autonomous islands, or will it all be accessible? That's a very big question. We also are very aware of all of the issues of cybersecurity, national security, industrial security, security of our kids, security of our finances, and that is now intimately associated with how our networks and clouds and apps all work. Canada has been an absolute leader in telecom since the beginning. Signal Hill in Newfoundland was the first radio transmission, and Anik 1, where's Bruce? There's Bruce. Anik 1, first satellite? A1. Okay. So, you know, we've been, you know, driven by our peculiar geography. We've been an absolute leader in telecom. You're talking to somebody who did 15 years with Bell Northern Research and Nortel, and another 7 running a telecoms research institute in Ottawa. We are not where we were on the world stage. And so part of the interest in the Academy is to, I don't think we're right off the horse, but we're kind of hanging by one stirrup. So we need to do one of those cowboy acts and, you know, spin ourselves back up onto the saddle. So one of the ways we're doing this, when back at the end of the 90s, I was director of disruptive technologies for Nortel, and we were working, within that portfolio was the university research portfolio for Nortel. So we worked because we were a Canadian company investing in universities, we were doing it in 17 different countries. We had almost 400 projects running simultaneously. To the academics in the room, I know most of your administrations from those days, but we also worked in China, in Europe, some interesting projects at the time that were going on in Russia. So it's a global it's a global initiative, but one of the things that was really interesting, I worked with a group called ICSI down at Berkeley, and of course, Berkeley in California at the time was the hub of innovation in the internet, and really responsible for where we came to. And what they did was they declared an architecture, and they said, as a researcher, you can adhere to the architecture or not. We're not going to tell you. But here are the APIs, so if you do work with the architecture, your piece of research can work with this other person's piece of research, can work with that person's piece of research. And so you became, the sum of the parts was very powerful. And so that's sort of the inspiration behind what we're doing at the moment, is to say we've got very active researchers all across the country and partners globally, but they're all working on a thing. So what we want to do is to define a national framework. We're not going to, I don't want to be as precise as a roadmap, but say these are the pieces we want you to think about. How do you integrate terrestrial and non-terrestrial networks? How do you integrate clouds and networks? And how do you manage all of this, which is one of the things that Lynn is going to be talking about. So the CAE is working with a bunch of people, and Al will lead off talking about that on what is this framework that Canadian, I will call it telecom, but there's a lot of data networks or other things. I mean, that's part of the problem. We don't really have a name for it. A bunch of people call it 6G. You'll have heard 6G. But 6G is more or less an interface spec at the moment. Like we leave it a bit fuzzy in definition, but it's much beyond, let's say, what the scope of 5G networks are. So that's sort of the view from the network, but at the same time, we've got all of this stuff going on in AI, we've got all of this stuff going on in quantum, we've got the satellites, we're making big progress in low-cost photonics. There's this nexus of all of these mega technology trends that you have to integrate. And at the same time, what you're trying to engineer for is not technical. So what we've picked as the 4 themes that define this, that you have to simultaneously satisfy, are intelligence, sustainability, accessibility, and trustworthiness. And I'll leave it to the other panelists to sort of expound a bit on some of those pieces. So we've been at this now for 2 years. We had a kickoff meeting at Carleton in Ottawa. Really good participation. We had very high-level government participation, and the sort of initial core group. And then we had another meeting October last year in Montreal, where 40 researchers got together and sort of broke into groups and roundtables and sort of came up with the first cut of this architecture. And then back in February, we had 15 companies, including the aforesaid Googles and Amazons and Bell and TELUS and Ericsson, who've played a huge role in this for us, a fellow who is the Malik Tatapamela, who is the Silicon Valley CTO for Ericsson, Red Hat, some what I would call non-traditional players, and they said, yeah, this is pretty good. Think about this, think about that. Ibrahim Gideon, if you know him, who is the CTO of TELUS, who is also a fellow of the Academy, former colleague from Nortel. So that's sort of where we are. We're making headway. We've got a big group of people. We're building links into the government and trying to understand what their needs are and talk to them through their lenses of artificial intelligence and quantum, which is really where their focus is, because these things are intimately tied. So that's sort of my introduction to this. I will sit down. I'm going to see whether Al is ready to go. There's Al. Hi, Al.
Hello.
So welcome to the conference.
Thank you.
We can hear you very clearly. Understand
Do you
it's
see my
a little later there. So
9 hours. It's still okay.
okay, so I'll take it away.
Given that yep. Okay. Thank you very much. We have limited time, so I'm going to just present 3 charts. Let the other speakers have their say, and hopefully we have time for question and answers after we're done. You can see my chart. Is that correct, Robert?
Yes.
Okay. So you see the yin and yang there, and that's because we're trying to do something synergistic in the sense of addressing challenges and opportunities in designing the new internet, if you will, and at the same time bring benefits to Canada. And so our discussions, as Robert said, has been going on for 2 years. We call our group as looking at sustainable and intelligent next generation systems, which you can call SINGs. And it's intentionally not 6G. There's massive investment in 6G, and we have an interest in addressing 6G, but our view is that the scope of what we want to address, especially if we want to address specific challenges in Canada, they have to be broader than 6G. So the yin and yang on the left, you have what's replacing the internet, or what the internet is becoming, if you will, which is a network cloud. And what's changed is that instead of being focused on the transfer of information through packets, where the emphasis has switched to supporting applications, services and applications. And sustainability is a key aspect of this, as well as intelligence. I'll explain that in a later chart. And in terms of arriving at a research agenda for Canada, we very much wanted to bring the research benefits to address challenges of Canada, and hence the right-hand side, network clouds for sustainability and intelligence. Sustainability, I'll explain in a second. We mean in a very broad sense, and then intelligence, of course, in the sense of AI and ML. So my 2 charts. What is this sustainable intelligent network clouds that I'm talking about? It's an infrastructure that is emerging out of the convergence of cloud computing and networking. As Robert mentioned, the hyperscalers, most of the traffic that runs on internet protocol runs on hyperscaler networks. But nevertheless, they're doing so using internet to support a variety of applications. And so what's happening as the networking and cloud computing become more and more integrated, this infrastructure is no longer just a network, it's no longer a cloud, it's a network cloud. One of the things that we're interested in, of course, there's a few companies that constitute the hyperscalers, but we're interested in greater participation from more players, and hence we're particularly interested in multi-domain platform that can involve many players, either as providing the cloud computing and networking, or providing the data and applications. We're interested in something, I won't dwell on this, it's possibly a little too technical, but what we call frictionless application creation. And what we mean by this is that up to now, the major applications are to a large extent confined within walled gardens of the hyperscalers. And we're looking for a platform that can foster the applications of a large number of applications by virtue of the fact that it's designed to make it easy to deploy new applications. Two essential elements of these network clouds. The first one is what we call near the edge computing. When you think of Amazon or Google or Microsoft, you tend to think of massive cloud data centers that tend to be far from the applications. What's happening now is that there are a large number of applications that are emerging that don't fit well with the model of going a long distance to where the data centers are. And this is by virtue of latency requirements, where the application has to be responsive during time periods that are much less than what it would take to traverse these distances to the data centers. And the other is that with the emergence of 5G, the cost of access bandwidth is reduced dramatically, and hence the ability to collect massive volumes of data is greatly enhanced. But it's still, that's in collecting it at the edge of the network. Getting that to the data center is expensive. And so an opportunity arises for developing a new infrastructure that's in what we call near the edge. It's in between that far core data centers and much closer to the applications. What applications am I talking about? Enhanced reality, virtual reality, connected vehicles, cybersecurity, cyber physical systems that involve monitoring and responding quickly, as in factories, for example. So all of these have this attribute that they're much better served, or they cannot be served by going to the core. So you need this near the edge computing, and that's a space that's not occupied right now by hyperscalers. And hence there's an opportunity to do the research and create new companies that can live in this space. The other has to do, and this speaks to 6G, is next generation access. Every generation for 4G, 5G, and now 6G involves enhancements in terms of the bandwidth, the amount of volume of information that can be transferred, but it's no longer just about the volume of data or the bits per second. The security, the resilience of the infrastructures are key components, and this come more in the form of a service. So access is no longer just about bits per second, but it's about bits per second with certain levels of reliability, availability, and that becomes a dominant concern in 6G. So in one chart, that's what we mean by network clouds. Now let's talk about how we can bring this to benefit to Canada. Okay, and so here, after much discussion, as Robert said, we've been discussing this for nearly 2 years. The focus is on sustainability and intelligence. Intelligence because of the strength that Canada already has in terms of AI and machine learning, and sustainability because there are important opportunities that are specific to Canada where this network clouds can be brought to bear. So the main point then is that we believe network clouds can support applications that can be used to promote sustainability. Part of what happens is as you go to cloud computing, and we believe certainly near the edge computing, that there can be massive economies of scale in the access and in computing that can enable these new capabilities. When we talk about sustainability, we usually talk about environmental sustainability, but if you look at the way sustainability is defined by the United Nations, there's three aspects to it. One is social sustainability, and this has to do with digital equity and diversity. And one of the ways that we believe this new architectures can help here is by providing choice and access to connectivity and services. So it's not just about receiving broadband access at so many megabits per second ubiquitously, but rather in different scenarios have the capability of obtaining the bandwidth, but along with associated services. And done properly, this can bring great benefits to education, health, public safety, smart cities, safe cities, and government. And of course, an area of great concern right now is not just security, but sovereignty of data. And the capabilities that can be built into these network clouds can help meet these security and sovereignty requirements. Then there's economic sustainability. And here we're talking about these network clouds can be brought to bear to support applications in many different settings, but we believe that if Canada is to invest substantially in network clouds, it should do so in use cases that where Canada has strength. And this involves mining, for example, resource industry, renewable energy, agriculture, and of course, finance. As well, in relation to smart cities, transportation, logistics, manufacturing, all of these have elements that involve collection of data, analysis of the data, recognizing demand, recognizing special events, and being able to generate commands that can adjust the infrastructure to best meet the needs of the given application. And finally, of course, oops, wrong direction there. There's environmental sustainability. And here, addressing climate change, monitoring and controlling carbon footprint, as well as various types of emissions, pollution, waste, water, all of these are elements that can benefit greatly from the ability to deploy sensing in a wide scale, to analyze this data, and then to produce beneficial actions that help further the objectives of these applications. So I'm going to leave it at that. Very high level. Our two next speakers will talk about some of the details, and I hope we have enough time to come back and discuss these questions that the audience may have. I'll pass it back to you, Robert.
Thank you, Al. Lynn, would you please join us? I do just want to reiterate, new fellow, congratulations.
Thanks. Yeah. Okay. Yeah. So in the past, starting from 2 decades ago, we have seen this convergence of two largest man-made systems. One is the internet, the other is the cellular systems, each with 1 billion users. And they combined into these all IP networks. And they provided the quality of service through bandwidth over provisioning in the wider network, as well as very sophisticated resource management in the cellular systems. And we have seen the evolution of cellular system from 3G to 5G. And now today, we find that the main driving force is this fusion of digital and physical systems in all dimensions. And this 6G will see lots of new opportunities and challenges. Next page, please. Yeah, first of all, like our traditional cellular system has already good coverage for our human population. More than 50% of human is covered. And the 6G will go even further. It will go to all kinds of unpopulated zones, remote areas. And in addition, 6G will cover our above water or underwater, which corresponding to more than 70% of our global Earth surface. And in addition, 6G will explore this altitude domain. So we will see like the network devices through this airspace, through UAVs, balloons, and the spaces through all kinds of satellites. And imagine the internet routers have very arbitrary topology, but those routers are fixed. And in future 6G, we will see this network topology like satellite network. Our Starlink have very regular constellation, but all these routers are moving in very fast speed. So the basic topology and the mobility features are totally different, which bring us lots of challenges and opportunities to maintain not only user mobility, but also support network mobility. Next page. Yeah. So 6G aims to support like all levels of human, cyber, and the physical systems interactions. So we can imagine the information receiver is not only smart humans, but also relatively dummy devices as well as algorithms, so on and so forth. They are less intelligent than human in terms of they are less resilient to error, delay, and losses. So this will bring this will bring more stringent requirement for our network. Our network needs to be more intelligent to ensure all these delay, jitter, service, and throughput, etc. This is currently not possible in the internet or 5G system yet. Next page. And when we have machine-to-machine, device-to-device, algorithm-to-algorithm communication, the information is no longer just point-to-point like our human devices to server, but also many other situations like we have multiple devices need to support one device, multiple sender to one receiver, or multiple sender receiver in a group setting. So in addition to the traditional unicast communication mode, we will see multicast, broadcast, in-cast, groupcast, we call it starcast. So how to support a starcast kind of service mode with service guarantee is another challenge. Next page. And eventually, like 6G is not only to deliver data bits from one place to the other place. We want to have this 6G to be more intelligent than that. We want to incorporate the communication capability with the data acquiring, which is sensing, data storage, which is caching, data processing, and learning from the data. So eventually, our future 6G and the internet, well, you can imagine it's a large-scale distributed system to support ubiquitous AI applications. Next page. So we can take a look of the current 5G architecture to see whether this 5G is good enough to support all these, deal with all these 6G challenges: ubiquitous coverage, quality of service requirements, and the starcast, as well as ubiquitous intelligence support. We find that current 5G has taken an architecture called CUPS, which is control plane and the user plane separation. The idea, in roughly speaking, is we try to move all the intelligence, all those control function into say cloud. So the cloud is like our brain to make all these control decisions, and those data can go through the mobile core. So mobile core devices are relatively dummy and simple. So this is the CUPS. And what's missing in this 5G architecture, we found that the current service is okay, but for the future service, we need to have guaranteed service for many real-time control applications. Then this kind of CUPS solution put all the intelligence into the cloud without the consideration of in-network intelligence is insufficient, because sometimes we need to have real-time control decisions to be made in millisecond level. and the cloud is far away from the network. The propagation delay could be hundreds of milliseconds. So it's not sufficient to just have all the intelligence in cloud. We need to have some real-time intelligence in network. So this is our argument. So in order to support this in-network intelligence, this is the new architecture we proposed. So in addition to this separation of data plane and the control plane, inside of the control plane, we divided the control plane into different levels. To the far right is we call the user level control. So those control like user association, billing, accounting, they can take seconds, it's fine. So we can put it into cloud. And in the middle is the session level control, like the session level authentication, mobility management. They can take tens or hundreds of milliseconds, so we can put it into cloud or put into edge. And then in the far left is our packet level or like flow level control decision maker. So these control functions need to be incorporated or can be combined with our data plane, attached to our data plane. And this is the place of our in-network intelligence. Next page. So with this cubic model, then the 6G architecture will look like that. So the control function which can tolerate a little bit of delay, like a user control or session level control, we can move those to the cloud or to the edge server. And then the packet level or flow level control function, we need to incorporate it into each devices from end to end. Next page. So to handle that, the like flow level or packet level control, so we found that these need to be done by more intelligent protocol, communication protocol. And if we take a look of our internet architecture, like the gas hour, like in the middle we have IP. This is one protocol for all kind of application without consider the application requirement. This is the one for all approach. And in the top and the bottom, we have many protocols to support many types of applications, particularly one protocol to one device, one application, or one protocol to one types of communication systems. So we have either one for all or one for one. But we found that like in the future 6G, in order to handle all those kind of dynamics, we'd better take the Lego approach, which is we try to decompose the control functions into building blocks, and we try to combine them in real time, and then make the protocol much more intelligent, and make the protocol to support all kinds of applications, handling all types of network dynamics. Next page. Okay. So this is an example of how we can decompose the network protocol. We use a transport layer protocol, for instance, TCP as example. TCP has 4 major control functions, and then each control functions, TCP takes one control mechanism, but we can develop many, many more different choices. Here is an example, like each control function, we can come up with 2 or 3 different choices. And then by combine them intelligently, choose each building block in each control, then we can come up with lots of combination, right? So if each of them has 3 choices, and the 3 to the 4, here we can provide 81 types of different services. So this is way much more intelligent than the current network protocol. Next page. So the key idea is once we decompose the control function, the major difficulty is which control block we need to use to handle all these application requirements and to deal with all kinds of network dynamics. Then we have a protocol control agent, which is in the control plane associated with each devices. For example, in the end system, the PCA, which is the control, which is the protocol controller, they can take the input from the top layer to bottom, from the application to physical layer, application layer's requirements up to the physical layer's measurements, and it can use simple or sophisticated AI or machine learning algorithms to make the decision to see which control block I need to use for each layer. Next page. So we can see that this control function adaptation and configuration essentially is algorithm is learning decision. Okay, we need to make the life simple. We can let each protocol have some like a cook menu, some default configuration as a starting point, and then based on the feedback and based on the application's requirements in real time, then we can do all these kind of reconfiguration and adaptation. So this is the idea, and eventually these are the learning problems. So we can use all types of simple learning problem like the bandit algorithm, or more sophisticated reinforcement learning or deep reinforcement learning to solve these problems. And this is actually a topic worth more exploration and exploration. Yeah, next page. So in the past given time, we don't have the time to do this. Based on this new protocol architecture, our team has worked on a few interesting 6G use cases and get some success. And we can, next page. And we also identify there are numerous open issues asking for the societies to come to support, like how we can decompose the protocol stacks and add a new control mechanism for each control function, so on and so forth. What's the best learning tools to configure and adapt all those protocols, and the cybersecurity issues, so on and so forth. Yeah, so I think I use up my time. Yeah.
Right on the minute.
Thank you.
So I think, sorry, is it possible to get, okay. So please, we're just trying to get the slides back up on the monitor there so that you can see what's being shown without having to.
Cannot be shown on the screen.
Okay,
Okay, great. Can I control the
yes,
page?
I think you can do
Yes.
it from that. He's almost there. And then if you need it bigger, he can expand it.
Okay, how to? I will go to the next page,
Forward
right?
and the red one's backwards.
All right, good.
While we're just getting the slides set up, I just wanted to mention, I mean, one of the interesting issues that Al talked about sustainability. I think the internet is now responsible for 6% of greenhouse gases, which is fine, except for the fact that it's still growing at 15 or 18% per annum. So it's every time you add more processing, you're adding more power. And so one of the questions is how do we get to where Lynn is talking about with less energy consumption? And it's a tough constraint.
Yeah, we need to consider the net gain. We have more processing in network, whether we can save some energy in somewhere else.
Yeah, absolutely. Okay, so it's now here. And
It's not on the screen yet. Oh, all right. Yeah, thank you.
yeah, he's going to advance it himself.
Okay, good morning, everyone. I'm Song Guo from Hong Kong Polytechnic. My background is in computer science. So today I would like to, from my view, personal view for the next generation. So my talk is on how computing power network innovates the world, a vision of future network. I cannot control it. Oh, okay. So actually, here is a little bit emerging technologies on we called generative AI. Actually, in the past 2 decades, AI has a big success in terms of answering questions like prediction, regression, or decision making. But in the past few years, there is a transition from those traditional capabilities to content generation in terms of languages, images, voices, videos using we called large foundation model. For example, ChatGPT, Delphi, the diffusion model, and so on. And all this emerging technologies have a very big impact for the network. So I just show a little bit on the information. Here, for those foundation model, the size in terms of number of parameters is over hundreds of billion parameters. In terms of inference, in terms of training, they need trillions of tokens as the training data, all right? And this number actually is increasing because human beings generate data exponentially. And also for the inference, if you look at the number of users in just compared to other similar tools, ChatGPT in just 5 days accumulated over million users. All this training, inference requires big computing power. And you can look at the right side figure, and the requirement for the computing power in the next few years is about tons of required than current power. So major countries over the world like China, US, Canada has their own initiatives to build up the computation infrastructure. For example, in China, we called computing net, a computing power network. In Canada, it's a digital research infrastructure strategy. In US, is a strategic platform, blah, blah. All right. All this eventually have a global understanding, and just very recently in the ITU, there is a standard. It's called Computing Power Network. It's a new type of network that realizes optimized resource allocation by distributing computing, storage, network, and other resources, information of services through a network control plane. So you can see that we have on the top users, on the bottom is resources, in between is a control platform. Right? So I will focus, in my talk, I will focus on that platform, control platform. And based on my own understanding and exercises and some preliminary studies, I will focus on 3 topics. One is networking for AI services. Second, AI for network management. And the third, governance for CPN and AI. So for each component, I will just highlight some interesting challenges and some of the existing solutions and what we have tried, and some promising results will be shown. All right, so for the first, ubiquitous computing power network for AI. Okay, so here actually these two objects, AI and networking in the future, it will converge. So AI will supporting computing for networking, and on the other hand, networking will support AI as well. So for computing power network for AI, that's straightforward, as I mentioned. The requirement exponential increasing in terms of data, in terms of users, in terms of demand of computing power. So here we actually, you can see some of the solutions is like predictable fabric for AI. I will give a little bit on that. Multi-cloud corporations for AI. Remember, Alberto also mentioned that, Internet of Cloud. And third is in-network AI. So I will give some of my understanding one by one. So predictable network empowers latency-sensitive AI applications. This is by application, AI application driven. For example, nowadays are using ChatGPT, right? And delay in terms is less than 100 milliseconds. In the near future, autonomous driving is less than 10 milliseconds. And for metaverse, the delay should be less than 1 millisecond. All this new emerging computing consuming applications require responses to be returned to users very, very quickly. And what we have studied is a solution we called deterministic network. So the basic idea is that we equipped the network interface chips with perception capabilities. They can understand the situation. They can do a very accurate prediction on the delay. And that sensibility is not in the core network. It's actually distributed everywhere, even in the edge. So all these smart switches have the sensing capability, and they can do very smart scheduling, make sure that the delay can be guaranteed, the requirement. All right, that is one core technology. The other is multi-cloud collaboration. Okay, this is also the network of cloud, right? The basic idea is that one single data center is not big enough, all right? So we need the collaborations. For example, the foundation model cannot be running on a single data center in the future, and they had to collaborate with multiple data centers globally, and that lots of challenges. For example, the traffic scheduling over the whole internet, and heterogeneous delay and resource offloading, many things to be studied. And the third interesting thing is we called in-network AI, which means that the computing and the communication will happen simultaneously. We don't, because in the future the I/O transmission of data will be a major bottleneck for the services to be provided. So the basic idea, we don't move data. Actually, we put computing capabilities near the data and do the computation, and eventually data will be consumed little by little in the transmission path. So eventually all this communication, computing, storage will happen simultaneously with the flow of services. So that is what we called AI for networking for AI. The second one is we are studying intelligence endogenous management for computing power network. And that idea actually is very similar to the 6G. So 6G, one of the difference of 6G from 5G is that intelligence apart native components of the technology itself. So we are not give a patch of AI onto the system. So in the future, next generation AI will be a native one. So here we've studied some of the recent results, for example, interoperability, security, and communication efficiency. Okay, some of the work already is happening. First, I would like to introduce how a foundation model can help automatic management for different systems to cooperate easily, seamlessly. So nowadays we have multiple vendors. Their protocols totally different, right? So if you have to configure the network settings manually, that would take a long time. And now we have the language model. They can understand the protocol. They can understand the manuals of protocol. They can understand written documentations of protocol. And they can do translation at the code level, so they can cooperate different devices, communication operators seamlessly. So that is happening. One of the results is shown in Google and also Huawei. Second example is foundation model invented by Google. And here the model we call the PaLM. All right, and the PaLM is a next generation of their original one, Lambda. So here, they actually embed security function into the model, and they can do automatic control on all perspectives of security threats. All right. Another one is by Microsoft. The product is called the Security Copilot. They actually can do the analysis in the real time, and also they can use their own software tools. For example, they're doing real-time analytics, and then they can use their functions. There are other Microsoft tools to do the security protection. Okay, so this is happening actually. And the third one is communication efficiency. So if we do communications because of the bandwidth limitation, we do huge amount of data. Before transmission, we do compression, right? And obviously, after receive the compressed data, some of information lost. And in video streaming, that is a very, very challenging case, for example, in the future online gaming, right? So here we are using a diffusion model. They can do recovery automatically and they can guarantee the quality. So also, our group is also doing on that direction, and I think they can actually beyond the limitations, what we call the Shannon limits, if the neural enhanced technologies can be embedded in the future. So because of time, I think I go quickly on the last part. The last part is a governance, because you will see many, many technologies, lots of users, lots of devices in the core, in the edge, right? Everything needs to be controlled, governance. So we're talking about a decentralized organization, trusted computing and communications, and on the top, we have to maintain a sustainable market. So the idea is from the definition of good governance, and not just on the technical perspective, many, many things because of AI, for the law, ethics, and many, many other digital assets and so on. So from IT perspective, I'm doing the blockchain, obviously one of the candidate for distributed decentralized governance method. For the trustworthy computing on the infrastructure level, for example, nowadays some chips provides function we call trusted execution environment, and also cryptography workload accelerator. They can protect security, privacy, and so on. At the algorithm layer, we are doing security multi-party computation, zero-knowledge proof, homomorphic encryption. All those new directions are very important to realize the vision in the future. The last one is the market, right? Because one domain of the governance is the participatory. So we would like to encourage all resources to be participated in the market. Needs to be fair, needs to be rewarding, right? And that's not only in the theoretical studies, but also other mechanisms needs to be incorporated in the networking. So our view is a global infrastructure for computing power, and the benefits will be for each and all users near the internet. Thank you.
If it's okay with Guy, I'll take a couple of questions and then we'll start. So what I'm hoping is for those of you who are in this space that we've piqued your interest, and for those of you for whom this is a little novel, maybe we've lifted the hood on what's behind your smartphone for the next 10 or 20 years, and then you can close the hood back down and not worry about it again. Yes?
So thank you very much for the interesting talk. So my question is about open source. How we can encourage researchers and companies to make their code available, data sets available for researchers? Because, I mean, it's getting at least network traces, network traffic data from companies, it's a thing. I mean, and you know the traffic pattern changes all the time. Even within the own company, they don't share them between groups. And if you are lucky and you are working with a group that they give you access, they make you sign, I don't know how many pages. So how can we encourage researchers and companies to make those available?
Yeah, I have the same trouble with that.
Yeah, I was going to say good luck. Al, do you have any thoughts on access to open data?
I didn't hear the question. Repeat it briefly. I'll try to.
Can you talk into the microphone and then Al can hear you?
So hi Al, I know you do a lot of prototyping. So how we can encourage researchers and companies to make their code open source as well as data sets available to other researchers?
Well, I think the trend towards open networking is and open source is actually becoming stronger with the Open RAN initiative associated with 5G. So that's good news in the sense that there's much greater interest from the telecom industry. In terms of research programs, as you indicated, I've been a firm believer in doing prototyping, doing testing by experimentation, and I think the including openness into the requirements of the funding, if you will, is a way that can help advance this. The open source approach is extremely useful in preparing graduate students because they get their hands dirty, they start experimenting, they start contributing, and it's a great way to get them started, both in learning but also in contributing to the open source efforts.
Okay, thanks, Al. I will say, you know, the general problem has been around for a long time, right? And getting companies to open up their real data has never been all that easy. Some of the large ones have their own test data that is sort of dummy data. But that, I would say, one of the potential values of the initiative, the SINGS initiative, as Al described it, is at least within the community and perhaps in shared communities, because it's an international effort, that it makes it easier for researchers to collaborate on, you know, if I'm generating data and you're generating control, can I use your data to try out my control stuff? And that's the value of building a community. But yeah, it's been an issue for as long as I remember, and I'm not expecting it to get better anytime soon.
Yeah, I think we can, like, as a community, we can try to encourage this kind of collaboration. And in the past, we have this experience. We have a few Starlink dishes, acquire a lot of measurement data, but these Starlink dishes, we only have 3, like in 3 different locations. And this is not representative to all kinds of situations. So we have tried to seek the community, those hobby lovers, and now we can access much more numbers of dish data, and we can leverage each other's dishes to do the measurements. So I think somehow we can encourage more, like within Canada, we can probably build up this kind of data sharing or experimental distribution systems. So like I can access your measurement data, you can access my thing like that. I think
I sense an NSERC application coming on. Yes, please.
My name is from York University. So I do have a question to Lin. So as a space engineer, it's good to see you list the Mars and the Moon in the 6G application. However, space industry is a little bit conservative, so people don't want to use the new technology. So how do you think the most challenge, the challenge to use the 6G in the future space exploration? Do you see any applications so far?
Yeah, good question. Thank you. So I should not put Moon and Mars, so I should stop at the satellite. And right now, the satellite applications has already been commercialized and very, very useful. Like in BC, we have so many rural area. They have we even don't have the road to reach them. So we need to fly to those locations, like those native conservatory places. So now our researcher brings satellite dish to them. Then they use satellite dish to help their agriculture, help their salmon fish monitoring, things like that. So lots of values there. Right now, the 5G cover all human population places, but in Canada we have so many places. The population is so low, we cannot use the traditional communication infrastructure. So all these space, like satellite communication system, is extremely valuable. And even in BC Ferry, right now we don't have internet access, but we bring our Starlink dish to the ferry, and we found a very good throughput and good put, and we provide free Wi-Fi service to all the other customers on boat, and they can all enjoy video streaming, etc. So we see lots of opportunities to have this space communication.
Okay.
If I may, one of the research opportunities has to do with what we call 3D networks, which is creating an umbrella under which different types of access can come in, and that especially is applicable to satellite and is very, very important to Canada.
Sohail, please, maybe use the microphone.
Well, currently we have seen that hackers come and control your computer, and then they say, give us $100,000, etc. So my question is, we are seeing a significant increase in control of what you can do, not only the computer, but major facilities, etc. So are we making ourselves more vulnerable to major disaster situation? Thanks.
Yeah, I think this is a very good, interesting, when I come up with my own protocol architecture, say we want to put more intelligence into the network, I come up with the similar question. So as a governor, do you like to govern lots of dummy people, or do you like to govern a society with all kinds of intelligent and adaptive people, right? So same thing for network. Previously, it's relatively simple because the routers, they do all these relatively straightforward things. If we want to have all these routers to be smart, to be adaptive, to be intelligent, then we need to have the designer to be even more intelligent, to consider all what can go wrong. So I think eventually, with more intelligent routers, more adaptive or more smart people inside the society, if we can come up with good policies for supervise them, eventually our society could be more efficient and more effective. So I'm still very positive to think about more intelligence inside the network.
Yeah, I think the traditional internet architecture kind of makes many of our applications sitting ducks, if you will. And part of it has to do with the fact that we don't have the monitoring capabilities built into the network. These kinds of attacks can be detected, but you have to have the sensing capability in place to collect the data. You need to have the deployment of the various types of analytics and training to do the anomaly detection. But these kind of things can be done, and I would say are in the pipeline. Now that doesn't mean that we shouldn't be looking at the next generation internet. Okay, as Robert, going back to where Robert started, it's been 40 years, and it's getting long in the tooth.
Okay, well, thank you very much. If you have other questions, I'm sure our panelists will be pleased to discuss them during the break. Thank you very much. Certainly, as you can tell, a topic near and dear to my heart, and I think it just permeates everything that we do as engineers. So really important that I think the Academy is informed on it and is regarded as a resource for where Canada is going on the communications. Thank you so much.